Hello everyone, welcome to Mindspan Education. Last video we were talking about the confidence interval and we looked at the interpretation of the confidence interval. In this video, let's try to construct a 95% confidence interval and the procedure will be same for constructing the 99% or 90% confidence interval. So we have this sample mean. We can think of this sample mean as a sum of these random variable divided by this term n, right? So recall from the central limit theorem that if we have the sum of these random variable, so we can think of the distribution of this random variable as a standard normal random variable using the central limit theorem, and not exactly this random variable. First of all, we have to make the standardized version of this random variable, and the standardized version of that random variable using the central limit theorem, we can approximate the distribution of the standardized version of this random variable as a standard normal random variable, right? So we are going to make use of this approximation, and so let me first of all make the standardized version of this random variable, that is x bar, right? And how we do that? So we have this random variable x bar, right? And this is the sum of these random variable, right? So first of all, we are going to subtract the mean of this random variable. So what will be the mean? So, and also we are assuming, let me first of all also mention that all these samples are, so all these x1, x2 and xn are identically identically distributed. All these are IIDs, right? And all has been drawn from the same population. Last video we have already discussed, right? So these random variables x1, x2 and xn are IIDs, right? So what I am asking is that I am trying to make this as a standardized version. So I am going to subtract the mean of this random variable, so each will have, and also we are assuming that whatever the distribution from where these samples has been drawn, and that will have the unknown mean, that is mu, right? And have the variance, that is sigma square, right? And these are the unknown quantity, and overall we are trying to estimate this mu, right, within a interval, right? If you recall from our last video. So each will have the mean mu, right? These x1, x2 and xn. So overall the mean of this random variable will, using the linearity, it will be n times mu divided by this term n, so n will get cancelled. So this will have the mean, that is mu, divided by what we do, we divide with the standard deviation of this, standard deviation of this random variable x bar. What will be the standard deviation of this random variable x bar? So let's first try to calculate the variance of this, then we will take the square root and we will have the standard deviation. So all these are independent and all these are identical, so the variance would be n times variance of this random variable x1, that is sigma square, right? And so we have scaled with this 1 divided by n, so here we will have 1 divided by n square, right? So recall the property of the variance. So if variance of x is sigma square, what will be the variance of a times x? That will be a square sigma square. Here we have the scalar quantity, that is 1 divided by n, so it will be 1 divided by n square. So this n will get cancelled, and we have to divide with the standard deviation. So the standard deviation would be root square of this variance. So variance is sigma square divided by n, so overall the standard deviation would be sigma divided by root n, right? So we are going to divide with the standard deviation, that is sigma divided by root n. Now this random variable is a standardized version of this random variable. Now we can make use of the central limit theorem, and we can say that this random variable will have a approximate distribution that will be a standard normal distribution. It will have the mean 0 and the standard deviation will be 1, right? So Now since we are approximating this random variable as a normal random variable, standard normal random variable with the mean 0 and the variance 1. So using the CLT, central limit theorem, we have this approximation, right? Now what we are going to do, so we are going to use this fact about the standard normal random variable. So what we are going to do is, so if we think of a standard normal random variable with the mean 0 and standard deviation with the variance 1, let's suppose we have this standard normal random variable, right? So what I am going to do, so we can treat this as a standard normal random variable, right? Using the central limit theorem, we can say that it will have the approximate distribution that will be a standard normal random variable, right? So what I am going to do, I am going to look at the standard normal random variable and I am going to see the or I am going to find the 95% of the probability where it is residing, right? So if you look at the standard normal table, so let me bring this standard normal table. So this is here, we have the standard normal table, and what the standard normal tables gives you, it gives you the probability that this standard normal random variable is less than some value little z, right? Basically it gives you the probability of this. So if this little z is this, then it will give you the probability of this part, right? So basically it is a table of the standard normal random variable, right? So if I look at the table and look at this probability, so we will have this probability when random variable takes the value 1.96, right? So we will have this probability when standard random variable takes the value 1.96, right? So what does it mean? It means that if the standard normal random variable takes the value that is of 1.96, then if we try to look at this probability, that the probability, let's say that standard normal random variable we are denoting with this z is less than equals to 1.96, and it will have the value that is 0.975, right? So what we are saying, that this part we are finding the probability of this, that random variable z takes the value 1.96, right? So this part of the probability is 0.975, and what will be the this part of this probability? So 1 minus 0.975, that will be, so this part will be 0.025, right? So if we have to look at this in terms of the percentage, so this will be 2.5%, right? Similarly, we can make use of the symmetry, and so this is 1.96, then here it will be, using the symmetry, it will be 1 minus 1.96, and this part of the probability, that is random variable z takes the value less than 1 minus 1.96, this part will be also have the probability that is 2.5% or 0.025, right? That means this interval will have the probability, or random variable z takes the value between these two, and this part will have the probability that will be, so 0.25% and 25%, that will combine as a 5%, and we will have the remaining 95%. Right, so ultimately what I am saying is that this random variable, that is the standard normal random variable, is greater than equals to 1 minus 1.96 and less than equals to 1.96. This will have the probability that is equal to 95%. Right, and we can write this equation as, or so this same event can be written as that the absolute value of z is less than equals to 1.96, and this will have the probability of the 95%. Alright, so here we are thinking this as a standard normal random variable. So we can use this fact that for the standard normal random variable, this is the calculation of the 95% probability. We can use this fact and we can write this like this, that the probability, so we are treating this as a standard normal random variable using the central limit theorem. So instead of writing z, we can write this. So the probability of this event, that the absolute value of this divided by sigma root over n, if this is less than equals to 1.96, so this will have the probability approximately 0.95 or 95%. Right, and this will be not the exact 95% because we are anyhow using the approximation, right? So the using the central limit theorem. But yes, we can make it, this is the beauty of this central limit theorem, right? Otherwise it would have been I think the unsolved problem. Right, now we can proceed, and so this, what we can do further, we will have to do some algebra, and we will have to find the upper limit and the upper bound and the lower bound for this mu. Right, so how we can proceed, we can bring this to left hand side, right hand side. So this event will be same as writing this event, that is less than equals to 1.96 sigma divided by root n. Right, and further what we can do, so this we can write as that this random variable x minus mu will be greater than equals to minus 1.96 sigma divided by root n, and less than equals to 1.96 sigma divided by root n. And we can do the further calculation. So then here we will not have this absolute sign. So now what we can do, we can multiply both side by negative, right? So this will be positive, and here it will be mu minus x bar, right? And this will be negative, and overall this can be written as, so I think you would be able to do that it will be 1.96 sigma divided by this root n is greater than equals to, so what I am doing is multiplying the negative side all over. It will be mu minus x less than equals to 1.96 sigma divided by root n. Now what we can do, we can add the, so we just want to have this mu, right? So what we can do, we can add this plus x plus x plus x So overall we will have x minus 1.96 sigma divided by root n greater than mu less than 1 x plus 1.96 sigma divided by root n. Alright, so this event, so how we have proceeded, we have used this fact of this standard normal random variable, and using the central limit theorem we have approximated this probability to 95%, right? And we have done some algebraic calculation, and ultimately this probability, the happening of this event or this probability, both are same, right? So now if you look at, we have here the upper bound of this mu or the sample mean or the interval that we were trying to find, right? It will have the upper bound, and this will be the this will be the lower bound, and this will be upper bound, right? So this will be x bar minus, and this will be x bar plus, right? And this is what the interval we were trying to estimate, right? So this event is algebraically identical to this event, right? And this statement tells us that there is a probability approximately equal to 95% that the confidence interval constructed this way contains the true mean of the unknown parameter or true mean of the population, right? Now if you would have to construct a, let's say suppose if you would have to construct a 90, so how do you construct a 90% confidence interval? This we have constructed for the 95% confidence interval. If you observe, you just need to find this number, right? And then you will have this number corresponds to the having or constructing the confidence interval for the 95%. And if you would like to construct the probability for the 90%, right? So you just need to look at, so this part have the probability that is 2.5%. So in order to construct the 90% interval, you want to have this part as a 5%, and this part will be 5%, and this interval will have the 90%. So you just need to see this, right? And if this is 5%, then this probability will be 95%, right? And if you look at this probability, that the probability this z is less than equals to 1.645, if you look at the table, the standard normal table, then this probability will be equal to 95% or 0.95, right? And we can say that the probability modulus of this z less than equals to 1.645 per 5, it will have the probability 0.90, right? So what is this mean? This means that 1.645 will be somewhere around here, and we are looking probability that less than of this point. So this will have the probability 95%, then this will have the probability 5%. And what is this means? This means that we are looking at the modulus of z. So less than 1.645, so z is greater than minus 1.645 and less than 1.645, and we have already seen that this have the 5% probability. Using the symmetry, this will also have the 5% probability, then this will have the 90%, right? You got it? So overall you will not have to do the same calculation. You just need to use here the value, that is 1.645, here 1.645 for the confidence interval of 90%, right? So ultimately you will have the normal table, or in the examination you will have these given values, right? Now if I would ask you, give me the 99% confidence interval, what will be the change each year? Let me know in the comment section. Now if you look at this expression we used to construct the confidence interval, you will notice that we need sigma, that is the standard deviation of the population, right? But the issue is that in most real world cases this sigma is not known to us. Why? Because this sigma is a population parameter, and the population parameter are unknown by definition. So if this sigma is given to you in the problem, fine, we can directly plug it in and compute the upper bound and the lower bound of your confidence interval. You will get a concrete numerical interval, right? But when the sigma is not known, how do we proceed? We have few options. The first option is use a non-parameter for a sigma. So there are few distribution for which we can have the upper bound of the, or the maximum value of the standard deviation. Let's assume that all these x's are, all these random variables are Bernoulli random variable, either they can take the value 0 or 1, right? So for the Bernoulli random variable we know that the expected value of this Bernoulli random variable is this little p, and this little p is the probability of getting the success, right? And in our case this will be equal to mu, right? And what's the variance of the Bernoulli random variable? That is p times 1 minus p. And what will be the standard deviation? That would be root over of p minus 1 minus p, p times 1 minus p, right? So we know the, or let me write sigma. So sigma, that would be equal to root over 1 minus p times 1 minus p, right? So p times 1 minus p. So for p is equals to half, that is when the probability is half, right? Then this standard deviation will take the maximum value, right? Because when the probability is half, we will have the more, in case of the Bernoulli random variable, we will achieve the maximum randomness, right? So that is why variance will be higher, so the standard deviation, right? So when p is half, right, and even you can find the maximum value of this thing, it will be the parabola, and it will have the maximum value at p is equals to 0.5. And what will be the maximum value of this sigma? The sigma will be less than equals to root over of 0.5 times 1 minus 0.5, that is 0.5. And here this value will be 0.5, right? So what we are doing, we are trying to get the maximum value of the sigma or the standard deviation. And for those distribution, if you are able to find the upper bound of the sigma, then we can make use of this sigma to find the confidence interval. And in this case the confidence interval will be little bit wider, but anyhow it is good, right? Because anyhow we do not know the sigma, right? But what the best we can do, is you can get the upper bound of the sigma, and again it will be not, you will be not always able to find the upper bound of the standard deviation for all the distribution, right? Like for the Bernoulli random variable, binomial random variable, or for those distribution, you will be able to find the upper bound of the sigma, right? So you can just put now this up, the maximum value of this sigma, and you will have the confidence interval, right? Now the second option that we can use is estimate sigma using the theoretical relationship, right? Let me give you an example. Let's suppose let me again take those random variables x1 x2 as a Bernoulli random variable, right? So the expected value of those Bernoulli random variables are this little p, that is the getting the success, this little p is the probability of getting the success, and this is same as saying that the equal to mu, right? So because we are anyhow estimating or we are considering the population parameter, or the mean of the population is mu, right? So that is the expected value of the population, right? So that is mu. Now we know the relation between, in case of the Bernoulli random variable, we know that the variance, that is the sigma square, is equals to root over p times 1 minus p, right? And that is equal to mu times 1 minus mu, right? Now this mu is anyhow not known to us, but what we are trying to do, what we can do, given the samples, we can estimate the mean of this population using the sample mean, right? And once you have this, then it will give you the estimate of your standard deviation, that is the sigma, right? So overall what we are trying to do here, we are simply trying to, if we have some relation between the standard deviation and the mean of the population, so using the sample we are estimating the mean, and once we have estimated the mean using the sample mean, then you will have also the estimation of the standard deviation, and then now we can make use of this estimated value of the standard deviation to find the confidence interval. Now the other option, so these are some special cases, right? If we have to find or get the value of this standard deviation in general, how we can proceed? So we can estimate the sigma directly from the sample, right? You will have this sample. So what we can do, we can directly estimate this variance, and once we have the estimate of this variance, you will have the standard deviation as well, right? So what is this variance? So this variance is nothing but the expectation of this random variable is the expectation of square distance from the mean, right? This is what the definition of the variance, right? Now if you see how we are estimating the true population of the mean using the sample mean. So this true population is nothing but the expected value of this random variable x, the whatever the distribution of the true or the population is. So this mu is nothing but the expected value of this distribution, that is the distribution of the population, right? And how we are estimating the value of mu using the sample mean. So now you will have these samples x1 x2 xn, and we can make use of the sample mean. So sample mean is the sum of the sample divided by the total number of sample. So this sample mean is the estimate of this true mean. If you take more and more sample, that means if you increase the n, ultimately this sample mean will converge to the true mean. You can just consider this as a fact. So even we can prove using some limiting theorem, but let's consider this as a fact that this sample mean ultimately will converge to this true mean if we take more and more sample, and if for the large value of n, this will be ultimately converging to the true mean, right? So this, what is this population mean? This population mean is nothing but the expectation of this random variable. What is this quantity? This quantity is the expectation of this random variable. Now how we have estimated, given the sample, the true mean, we can simply estimate this quantity as well. So we will have these samples x1, x2, x3 or xn. We will have this sample. So how we can estimate this? Now instead of summing the x1, x2, now we will sum this random variable, that is from xi minus mu ka whole square, and then we will divide or take the average of this random variable by dividing the total number of sample, right? So this is the estimation of this quantity, that is the estimation of the variance. So let's denote as hat. But the problem is here again, we have this unknown, that is the true mean, right? So we have this sample. What we can do, we can even estimate this true mean. So now we will have this expression from I is equals to 1 to n xi minus, instead of using the true mean because that is anyhow unknown, we can estimate using the sample mean. So sample mean is x bar ka whole square. Now here one point to note, if we are trying to estimate the variance from the sample, then this factor that we use is not n but n minus 1. So we use this scaling factor n minus 1. So anyhow, whatever the factor you use, 1 divided by n or 1 divided by n minus 1, for large value of n, the estimated variance will converge to the true variance of the population, estimate of the sigma directly from the sample. Now you see this estimate that we are making of the sigma. So we now this is sigma square, that is estimate of the variance. If we have to find the sigma from here, that is the standard deviation, we can just take the square root of that and we will have the sigma. Now here the important point is that, so we are using here the sigma, and that this estimated sigma depends upon the sample, right? So if we use this estimated sigma to calculate the confidence interval, right? So now here we are introducing more randomness, right? Because we are not using the actual sigma, we are using the estimate of it, and that estimate itself depend upon the sample, right? So this additional randomness affect our confidence interval, right? So we need to account for that. And how do we account for that? So when we estimate sigma from the data, we cannot use the standard normal distribution, right? So like here we have calculated the value, that is 1.96 using the standard normal distribution, right? We cannot make use of this 1.96. Instead we have to use the t distribution, right? And which is the corrected version that accounts for this extra variability, right? So this t distribution, so we will go through this t distribution in next lecture. So so if this is a normal distribution, the t distribution will have the more probability in the tail, right? So the tail is heavier. So we will go through the t distribution, you will have the idea. So instead of using this 1.96, we might get slightly bigger number, right? Maybe 2.04 or 2.23 depending upon your sample size, right? So this correction becomes especially important when the sample size is small. Usually the sample size is less than 30. For the large n, the t distribution and this normal distribution become almost same, so the difference will become negligible, right? So if we have the sample size that is less than 30, what we the value that we will get here is from the t distribution, right? And if this sample is large, then the t distribution anyhow is going to converge to the normal distribution. Then doesn't matter if you are using the t distribution or the normal distribution. But for the smaller sampler, we are going to use the t distribution in order to find these values, right? Now if we let's proceed with problem, but before we proceed with problem, let's have a look at the t distribution and the chi distribution as well. We will go through these two distribution and then we will jump to the problem of these confidence interval, right? Anyhow, we can directly jump to the problem, there is no issue. Just we need to look up the table and we need to see the value, this critical value, that is all, right? Otherwise but anyhow we have in the syllabus that we need to go through the t distribution and the chi square distribution. We will go through that, then you will have at least idea about the t distribution in comparison, or even you can see this t distribution and this normal distribution, and you can compare that how this t distribution is related to this normal distribution, right? And how it varies as we take more and more sample. All right, so let me give you the summary. So here we have the G confidence or Z confidence interval for the mean when sigma is known. So you can just find out if this sigma is known, right? You can just simply put it this sigma and you will have the confidence interval, right? And here there are few notations that I think while going through I haven't introduced these notations, but I have used these notations, right? So let me go through first of all these notation. So here if sigma is known, you are going to use simply the normal distribution to find these values, right? So in case of the 95 confidence interval, these values that we have found, these values are nothing but the critical value, and we have found that it is nothing 1.96, and if it is we are calculating for 90% confidence interval, these values will be 1.645 in case of the if we are using the normal distribution, right? And if sigma is unknown in that case, and you are and we are estimating the standard deviation from the sample, then in order to adjust this randomness or this variability, what we use is the t distribution, right? So in that case we will be looking up the t distribution and using this critical value, right? So here it is 1.96, right? In the t distribution it will be more, so we will see once we will go through the example. And one more thing I want to mention is this. So this is the estimated estimation of the standard deviation, right? So this is estimation of the standard deviation, right? So you will have the sample and you are going to estimate the standard deviation this way, right? So this is the estimation of the let me also use this here s square, right? So s square, and now if you want to have the s, then you will just take the root square of this and you will have the estimated standard deviation, and you are going to make use of here, and then in that case you are going to use the t t distribution table, right? Usually we use this t distribution table when the sample size is less than 30, right? And if sample size is larger, then doesn't matter if you are using this confidence interval or this confidence interval, both will be same, because for large value of n, this t distribution will converges to the normal distribution, right? So I think all the terms here are clear. So, and these are the estimation of the population mean. So these are what are these? These are the sample mean. That is the estimation of the population mean. Let me write here estimate of the population mean. Estimate of the standard deviation of population. Right, and this alpha, so if this 1 minus alpha is the confidence level, then this alpha will be the complementary of the confidence level, or we also refer it as a significance level, right? So if the confidence level is 95%, then this alpha will be 5%, right? So this is the complementary of the confidence level. All right, I think you should have now the sense of the confidence interval. We have gone through the interpretation. We have gone through that how to construct 95, 90 or 99% confidence interval of a sample mean, right? Next we are going to look at the t distribution and the chi-square distribution. We will just have an overview of these distribution, and then we will jump to the questions based on the confidence interval. And the last thing that will be remaining is the hypothesis testing, and soon we will finish it up, maybe in 1 or 2 lectures, and then we will be end with the probability and statistics for the GATE DA paper. That is all in this video. Thank you so much.